Hello, my name is Brandon Gilroyed. I'm an associate professor in the School of Environmental Sciences at the University of Guelph. Today I'm going to give a presentation on the potential role of anaerobic digestion in reducing greenhouse gas emissions from the dairy industry. This slide is an overview of the talk that I'm going to give. So first I'll start with an introduction about myself and my background. We'll discuss a little bit about the scope of the problem in terms of greenhouse gas emissions globally, as well as specifically to the dairy industry. And then we'll get into a discussion about anaerobic digestion and the potential ways that it can help move us towards carbon neutrality in the industry, including some case study from my own institution. And then we'll wrap it up with some concluding remarks. I'm recording this presentation from Canada, from London, Ontario, but I actually grew up in Alberta, a very rural area. Not a lot of dairy there. It's mostly a cattle-based community. I did all my education in Alberta, and then I moved out to Ontario to the University of Guelph, where I work in the School of Environmental Sciences. My research interests are fairly diverse, but anaerobic digestion is at the core of our research program. We're fortunate enough to be able to investigate 80 processes at a variety of scales, from small benchtop to pilot scale, all the way up to commercial scale, 250 kilowatt system installed at the U of G Ridgetown campus at our dairy farm. We investigate a variety of things related to the process itself, feedstocks, pretreatment technologies, particularly for lignocellulosic feedstocks. We have other research looking at various other types of waste valorization, production of bio-based platform chemicals such as lactic acid and succinic acid. And we also have a arm of the program that is focused on animal mortality management strategies, both routine and emergency. And that also includes aspects of anaerobic digestion. If we think about solar energy, photons are carrying solar energy to Earth from the sun, almost 150 million kilometers. A very small portion of that energy is captured in photosynthesis and stored as chemical potential energy. And that chemical potential energy passes through the food web. So in this example, from sunshine to corn, corn to cow, cow produces milk, and then people drink the milk. So we're all ultimately derived from that solar energy. And of course, over time, there's a certain amount of biomass that doesn't participate in the shorter carbon cycle. And these are the things that become fossil fuels, which are a big repository of solar energy. If we look at the global carbon cycle, we can see the contributions of human emissions. The numbers shown are in gigatons of carbon per year, and if you see the numbers in red, those are impacted by human contributions. Numbers in yellow are natural fluxes, and numbers in white represent stored carbon. So most of the carbon in the global system is locked up in rocks and in the ocean. While the scale of human emission is small relative to the other fluxes, the reason this poses such a risk is because we're taking carbon from fossil reserves and putting it into the atmosphere. And of course, in the atmosphere, CO2 serves as the major source of global warming. In the animation on this slide, we can see the increase in mid-tropospheric CO2 concentrations in the atmosphere over time between 2002 and 2017, consistently increasing over time, and fossil fuel consumption is the main driver of anthropogenic contribution, including electrical and heat production, transportation, and industrial manufacturing, and of course, agriculture. In the second animation, we can see trends in global temperature over time between 1880 and 2020. And The main trend, of course, is warming, particularly in the 21st century, rapid increase in temperature. As we've seen, atmospheric CO2 concentrations have increased rapidly since industrialization due to anthropogenic contribution, and we've also seen an increase in global temperatures, particularly in the last 20 years. And all of this has contributed to increased ice loss in polar regions. This poses a threat not only due to rising sea levels, but also by forming a positive feedback loop where there's less ice available to reflect sunlight, resulting in increased absorption of solar radiation and further ice loss and warming. So on this slide we can see the global greenhouse contributions by sector. In the top panel it shows the current weighting of emissions over time of the three main greenhouse gases: CO2, CH4 or methane, and N2O or nitrous oxide. In the leftmost panel you can see that CO2 has the biggest impact, particularly over a longer time horizon, years after emissions. In the rightmost panel, you can see that methane in the short term has a significant impact that decreases over time as methane is broken down in the atmosphere. In the bottom panel, we can see contributions by sector. And so the leftmost part is global warming potential over a 100-year horizon, and in the center, over a 20-year horizon. So agriculture, which is the green slice of pie, is making a significant contribution in both time horizons, but more so over the 20-year period because of the contribution of methane being more acute in the short term. The previous slide, the data was based on the IPCC 2014 report, which reflects global numbers. On this slide we can see greenhouse gas contributions by sector in the United States. And here agriculture is making a smaller contribution, so 10%, with transportation being much higher percentage within this portfolio. The lower percentage of greenhouse gas emissions from agriculture in the United States and other Western countries that are heavily industrialized reflects the reduced carbon intensity of production in those systems. In this slide, if we look specifically at methane emissions by sector in the United States over time, we can see that overall emissions of methane have decreased between 1990 and 2018, but the relative contribution of agriculture has increased over that time, and that's due to increased intensification of animal production. If we focus now specifically on the dairy sector, globally, GHG emissions have increased over time between 2005 and 2015, and methane in particular has gone up, and this is in spite of the average emission intensity of milk production declining over that same time period. So becoming a more efficient, lower emission intensity, but production as a whole has increased, and so that's led to an absolute increase in emissions over time. If we look at the breakdown of greenhouse gas emissions from dairy production globally, the biggest proportion is from enteric fermentation, which is probably the most challenging to do something with in terms of mitigation. The focus of this talk is on anaerobic digestion, and it has the potential to impact several of these categories. The most obvious one is related to manure management, so mitigation of methane in particular, but also nitrous oxide. The next potential reduction is in direct energy and indirect emissions of CO2, depending on how the biogas being produced is utilized. Most applications have an energy component. And finally, there's opportunity for reduction of emissions related to production of feed, both nitrous oxide and carbon dioxide. This is based on reutilization of nutrients coming out of the anaerobic digestion process as crop fertilizer. One of the most important things to keep in mind is that application of anaerobic digestion on dairy farms has potential for mitigating greenhouse gas emissions in other sectors. So it's not only potentially impacting those emissions from agriculture, also has ramifications for the transportation sector, electrical generation, even industrial, commercial, and residential use. This is a brief overview of the anaerobic digestion process, and for people with a dairy nutrition or rumen microbiology background, it'll look very familiar. It's the same process that happens in ruminants. Anaerobic digesters are sort of like much less efficient versions of cows. And so we have complex organic materials composed of carbohydrates, lipids, and proteins being hydrolyzed, being converted into acids, volatile fatty acids, and those are broken down into hydrogen, CO2, and acetate, which are eventually converted into methane and CO2. And there's also potential for generation of hydrogen sulfide in these systems, which is undesirable if we're making biogas because of the corrosive properties of H2S. Of course, whether it's in the rumen or a biogas system, it's a microbiological process, and so there are different phases that are constantly need to be in balance with one another. And so if methanogenesis is reduced, you can see an increase in volatile fatty acid accumulation, which can cause a drop in pH. And so in cattle, this would be acidosis. And in a biogas plant, it's a sign of impending process failure. While a cow can self-regulate how much they eat and when, biogas plants are operated independently, and the operators can't see or feel in real time when these disasters are pending. So it can lead to a significant loss of uptime. Not being able to detect when the system has come out of balance. This is an overview of how an anaerobic digestion process works. Anaerobic digesters come in a lot of different configurations, continuously stirred tank reactors, plug flow reactors, upflow reactors. There's a lot of different design options, different scales, depending on the process, but they all are operating on the same principle, and that is that they're containing that microbiological process that discussed in the previous slide. So a wide range of inputs can be used as substrates for biogas production. So it can be manure from livestock production, it can be energy crops or crop residues, it can be food waste, it can be wastewater. All of those things are serving as carbon and nutrient sources for the process. Within the anaerobic digester, the combination of microbes are breaking that material down into biogas, which is principally composed of methane and carbon dioxide. And the methane is what we're after there in terms of energy. So it can be directly combusted and used for heat. It can be combusted in a generator to produce electricity, or a combined heat and power unit to produce both. Alternatively, the biogas can also be upgraded to biomethane by removing the CO2, leaving us with a gas that's 96% or higher methane. So it's can be considered renewable natural gas, and that can be used as a transport fuel for vehicles, or it can be injected into the natural gas grid for utilization any way that we normally use natural gas. The other important component coming out of the digester is the digestate, which is the they're liquid and solids that aren't converted to biogas, and those can be applied back to agricultural land as a fertilizer or soil amendment. Some facilities have a solid separation process, like a screw press, to pull out any residuals, and that can be used for livestock bedding as well. One of the really attractive features of using dairy manure for anaerobic digestion is that it's a very good substrate, not so much in terms of energy, but in terms of the microbiology and the buffering capacity that it brings. And from a greenhouse gas emission standpoint, we're avoiding methane emissions normally associated with manure and producing an energy source, so biogas or the biomethane, which in turn can be used to offset emissions from other sectors. So we can be carbon neutral or even carbon negative potentially. So this biogas, biomethane from manure has a very low carbon intensity, which is very attractive. Anaerobic digestion offers a number of potential benefits for the dairy industry. So whether it's energy capture through combustion of biogas to produce heat or electricity, or upgrading it to renewable natural gas for later combustion, represents efficient use of feedstock. And if we think back to solar energy, we are just utilizing more of that chemically stored energy that originally was stored in corn plants or whatever our cattle feed was. We're just making sure that we get as much of that energy out for our use as possible. Of course, from a greenhouse gas emission standpoint, we're avoiding most of the emissions that would normally be associated with manure in terms of methane. There is still potential for fugitive methane emissions from biogas plants, and we need to make sure that we minimize those to maximize the benefit. There's also evidence of reduced N2O emissions from anaerobically digested manure. But that is a little bit situational, and so under certain situations there could be increased nitrous oxide emissions, and so that's important. The same can be said for ammonia. So most nitrogen that is in digestate is going to be stored as ammonium, and so there can be increased ammonia loss from digestate compared to manure, depending on the situation. Certainly when it comes to land application, that nitrogen will be highly mobile, but also readily usable by plants, and so the timing of application will be important to minimize nitrogen loss. Nutrient cycling back to farmland in the form of digestate is an important part of making this a circular process. One of the really nice things in terms of co-digestion with off-farm substrates is that things like food waste that normally might not get back to agricultural land would be cycled back, and this reduces reliance on inorganic fertilizers, which have a high greenhouse gas emission associated with their production. On a previous slide, we mentioned that separated solids can be used for animal bedding, so this is a small cost savings depending on the animal management system being used. And finally, there's a significant reduction in odor and some reduction in pathogens in manure that is anaerobically digested. The pathogen component really depends on the type of pathogen in question. So some organisms are reduced, 2 to 3 logs in anaerobic digesters, and others are not impacted at all. So something like E. coli tends to be fairly susceptible. Things like Clostridia or spore formers are generally not impacted significantly by the anaerobic digestion process. More infectious things, for example, prions, which cause BSE, are not significantly reduced in anaerobic digestion systems. And so materials containing or potentially containing prions shouldn't be digested without some sort of thermal or alkaline pretreatment. One of the things that I think is most attractive about anaerobic digestion is that it's a fairly low-hanging fruit, so it's a mature technology. It's been around in some form for a couple of 100 years. Certainly industrially, it's widely used around the world. So the process is scalable from very large multi-megawatt installations down to very small installations. The photo here is from a farm in Ontario where they milk 65 cows, and they're running this pocket digester, and they have two 10 kilowatt engines, one selling electricity onto the grid and one using or one providing electricity for on-farm use, and that system has been operational for a couple of years. Of course, countries like India and China, there are millions of very small household scale digesters that work to provide cooking gas for families. So the process works at really any scale. It comes down to economics for what scale will work depending on where you are. The process is flexible in terms of the inputs, so dairy manure is a great baseline material to put in, but you can put a wide range of other organic substrates in depending on geographic location and things like tipping fees or what is available. There's a lot of flexibility in the end use, and so conventionally we talk about biogas for electrical production or heat use, but renewable natural gas is a big upcoming topic, and there are other more novel things that we'll touch on later that the process can be used for. And finally, one of the other really attractive things about anaerobic digestion, if we're thinking forward, is that it is very easy to integrate with other renewable energy technologies. So whether it's biodiesel production, biodiesel, about 10 or 12% of what is converted ends up as waste, glycerin, and that's a very good substrate for anaerobic digestion, so you can make biogas from it. The concept of power to gas, so storing renewable energy sources such as wind or solar energy as methane, something we'll discuss towards the end of the presentation. And potential for integration with thermal processes, so things like pyrolysis or steam reformation. Some materials aren't suitable for anaerobic digestion. They just won't break down, at least in fast enough. But they could be suitable for thermal processes, and so there's potential for integration of those. There's a lot of research out now showing that including biochar, which is produced during pyrolysis, has beneficial effects for anaerobic digestion, making the process work more efficiently and more stably. And there's also potential for CO2 capture and storage, which would really push the carbon intensity of any biogas or RNG produced out of these systems into negative territory, which is very attractive. Anaerobic digesters have the potential to serve as the hub of biorefineries. Biorefineries are taking biomass of some sort and producing value-added products, but most of those things are also have residuals that are good candidates for utilization in anaerobic digestion. One technology that I wanted to touch on that's just becoming commercially available is based on this idea of gas to power. And so in this concept, we're utilizing carbon dioxide produced during anaerobic digestion or any other process that generates CO2. But in this discussion, we'll use an anaerobic digester. The CO2 is being produced, and then we're utilizing low carbon intensity electricity, or it could even be stranded power that's become redundant. And we're using that to electrolyze water, so to split water into hydrogen and oxygen. The hydrogen produced from electrolysis is combined with carbon dioxide in a biological methanation process, and that results in the production of methane, um, which can be used anywhere that we would use renewable natural gas, so for heating or transport purposes. The really interesting thing about this concept is that it enables us to essentially store electrical energy as chemical energy. So issues with wind power are that the wind doesn't always blow, with solar power that the sun doesn't always shine. And so having a viable storage mechanism for energy produced by those technologies offers incredible benefit potentially. If we think back to the anaerobic digestion process, the final step in hydrogenotrophic methanogenesis is combining hydrogen and CO2 to create methane. This is done by a type of archaea, and so this methanation process is biological in nature. This concept of power to gas has existed in literature for a number of years, but just now we're starting to see commercial scale demonstrations popping up in Europe and the United States. We've now walked through the anaerobic digestion process and discussed some of the potential benefits. So I thought we should do a bit of an overview of the state of the industry in various parts of the world. So in this slide, we're looking at biogas and biomethane plants in the European Union. Europe is considerably further ahead than North America in terms of the number of plants and energy production from anaerobic digestion. So almost 19,000 plants in the most recent report in Europe, representing 167 terawatt hours of production annually, and 725 biomethane plants. So these are plants that are upgrading their biogas to RNG quality, representing 26 terawatt hours per year. Forecasts in the EU are to double this production, which is already considerable, by 2030, and to over quadruple production by 2050 as they try to reach net zero targets for that date. If we look at the figures here, the top right panel is showing the number of biogas plants built, and we can see that that number's been plateauing for the last 5 years or so. But in the bottom right figure, we can see that biomethane plants continue to grow, so 16% in the most recent year-over-year. And agricultural feedstocks are dominant in both systems, although there has been a shift away from energy crops in general. If we shift to North America and look at the United States, currently approximately 2,200 biogas sites in the country. Only about 250 of those are on farm, according to the American Biogas Council. So there's substantial potential to add more sites. So estimates of around 15,000 new sites, including over 8,500 on farms. And the states with the biggest potential to add biogas energy are California, Texas, North Carolina, so big agricultural states. And if all of these sites were built, estimates are that this would meet the energy needs of roughly 3 million American homes, so a substantial amount of green and renewable energy. My area of expertise is not focused on the United States market, but I think there are some similar barriers to adoption of biogas in the U.S. As with Canada. One of the big ones in the U.S. is the level of commitment to biogas. So conventional gas is very inexpensive right now, and so that's a big challenge. One of the reasons that Europe is so far ahead in adoption is because of incentives that have been put in place, so subsidized policies, and also general societal desire to shift towards renewable energy and greener energy sources. Investment is a big issue, so uncertainty in market conditions is one of the big ones. And I think anaerobic digestion in general is undervalued in terms of the total benefits offered. Right now, basically only what we can sell the gas for returns economic value. There are also challenges with jurisdictional issues, so inconsistencies between local, state, and federal agencies. And there's a general poor awareness of the benefits of anaerobic digestion. So much attention gets paid to electrification, things like wind and solar, other renewable energy technologies. In the transport sector, certainly all of the buzz is about battery-powered electrics, even fuel cell electric. Very little talk about renewable natural gas as a viable option for things like transit, transport, heavy transport. Shifting our overview now to the Canadian biogas sector, considerably smaller again than the American sector, and certainly much smaller than Europe. So 61 agricultural and food waste digesters, 86 wastewater treatment facilities, 53 landfill projects. There's considerable interest in building biogas facilities in Canada, but depending on the province, it's a very difficult economic climate. There's just not a lot of incentive out there to invest in capital projects. And for that reason, we've seen a bit of a stagnation in growth of the industry. Some of the barriers to adoption in Canada are similar to the US, so investment is a big one, and it's because of uncertainty with market conditions. In Canada right now, we have a lot of new regulations coming in, so the Clean Fuel Standard was just released. There's a federal greenhouse gas offset program that's going to be coming in shortly. And then there's the carbon tax and the incremental price increases there. So there's a lot of things changing, and no one really knows yet how that's going to look for gas producers and whether it will encourage the capital investment necessary. Again, the total benefits of AD are generally undervalued or not valued at all. In Canada, we have additional logistical issues, low population density, smaller farms, certainly for the dairy industry. The size of the farm is much smaller than we would see in the United States. And so there is interest in, investigating whether or not a 40-cow dairy can be viable as a site for an anaerobic digester. And I'll talk a little bit more about that later. Canada, similar to the US, inconsistency between jurisdictions. Some challenges just, talking to the different utility operators in different provinces. So everyone is interested in renewable natural gas, but the utilities are similar to the gas producers, that they just don't know quite what to expect at this current time with all the changes in policy happening. I'd now like to give an overview of the anaerobic digestion facility that I oversee as part of my job at the University of Guelph Ridgetown campus. So this facility was built in 2011, operating since 2012, and selling electricity to the provincial grid since 2013. On campus, we have a small dairy, milks 40 cows, tie stall, a liquid manure storage system. All the manure from the dairy goes to the anaerobic digester, and we also receive brown grease from an off-farm supplier. So that's grease trap waste from restaurants predominantly. The biogas that we produce is burned in a combined heat and power unit. and the electricity is sold to the provincial grid at a subsidized rate of 22.2 cents per kilowatt hour, and the contract for electrical generation is for 20 years. So we are feeding approximately 15 tons of liquid dairy manure per day and around 6 tons of that brown grease substrate. Digestate that is produced during the process is applied to our farmland on campus, and excess that we have is distributed to cooperators that are in the immediate vicinity of the biogas plant. One of the things that I learned preparing this presentation is that we're actually not very well equipped to quantify the environmental impact of our facility. So we know how many kilowatt hours that we produce annually, of course, and this is enough roughly to power 90 homes for the year. If we use a carbon intensity for Ontario electrical production of 40 grams of CO2 per kilowatt hour, we're mitigating roughly 39 metric tons of CO2 per year. So in Ontario, the power mix is composed predominantly of nuclear and hydropower, but there is also a significant portion that's made up by gas, and that increases the carbon intensity. Of course, the benefit of biogas production in terms of carbon avoided from electrical production varies by region. So in Canada, carbon intensity of electricity is extremely low in Quebec, which is entirely hydropowered, compared to, for example, Alberta, which, at least at the time of this figure, was still using a large amount of coal-fired electricity with a much higher carbon intensity. I would like to preface this slide by saying that this is not my area of expertise, talking about greenhouse gas emissions and utilizing models to calculate these things. But I did put in some very simple numbers into the HOLLOWS program, which was developed by Agriculture and Agri-Food Canada to estimate methane mitigation from manure at our dairy. And so, again, just using rudimentary numbers, the program estimated 70 tons of CO2 equivalent emitted from methane related to manure. And then if we switch from a liquid manure storage to anaerobic digestion, we saw a reduction to 4 tons of CO2 equivalent. I didn't include any methane mitigation from the off-farm feedstocks that we receive. That would be difficult to calculate for brown grease because there's a variety of other end markets where it could go and different emission factors associated with those. So within the HOLLOWS program, the total GHG emissions for our dairy were estimated at 255 tons of CO2 equivalents without anaerobic digestion, and that was reduced to 189 tons with anaerobic digestion of manure. So if we take in the CO2 equivalents mitigated through electrical production, add in our methane mitigation credits, we end up with 105 tons of CO2. In conclusion, it's clear that there's an urgent need to reduce greenhouse gas emissions across all sectors, and certainly agriculture has a part to play in that. I think agriculture has a real opportunity to be a leader in this area and to contribute to emission reductions in a variety of other sectors by adopting technologies like anaerobic digestion. AD itself is a proven and mature technology for mitigation of emissions from manure and other organics. It has the flexibility and adaptability to use a variety of inputs and outputs. So it can be used to support renewable electrification. Um, it also offers a terrific opportunity for diversification of energy, so conversion to electricity, conversion to renewable natural gas, conversion to hydrogen, the concept of power to gas. So a lot of potential avenues to meet the variety of needs that we have, whether it be electrical generation, heating requirements, transportation. There's something there for all those areas. Another really attractive thing is that it works with existing electrical and gas infrastructure. So it's a technology that is plug and play right now. All that being said, there are significant barriers to adoption in North America right now, primarily related to market conditions and undervaluation of total benefits. So hopefully, at a policy level, some of those things are rectified through appropriate incentives, um, so that we can see an expansion of the adoption of this technology. There's some lofty international goals. So attempting to get to net zero by 2050 is it going to require a huge heavy lift from all sectors of society, and agriculture certainly can play a role in reaching that. Um, we also have to consider feeding 9.5 billion people by 2050 without increased resources, and so this means we have to be more efficient. So methane emissions represent an inefficiency in energy, and tool emissions represent an inefficiency in nutrients. And so reducing both of those emissions has a variety of benefits. I'd like to thank the conference organizers for the opportunity to present on this topic, and thank you to the audience for your attention and taking the time to sit through the presentation. If you have any questions, any interest in collaboration, any thoughts or interest in doing a pilot or demonstration project, or if you're a student looking for an internship or prospective graduate studies, don't hesitate to contact me at the email address provided. Thank you very much for your time and attention.